So in this video, we're going to talk about the enthalpy change for a reaction. Okay, we're not talking necessarily for a formation reaction. We're not necessarily talking about any particular reaction. We're just talking about for any reaction overall. And this has a foundation in Hess's law. Okay, but regardless, this is the formula for and I'm going to get rid of my calculator here. Okay, so this is the formula for what we use to calculate the enthalpy for any reaction. Okay, and so a lot of times we will use the formation reactions to get the delta H of formation of all of this stuff. Sometimes we can really, because of what a formation reaction is, sometimes we can just go to tables and get that thermodynamic data. So let me show you what we can get here. So here is a table. I just went to this excuse me, to this website, chem.uri.edu. I like Bilbo Baggins, so that's good. So if we notice that every delta H that is given, it's the delta H of formation. And so that's because of the nature of formation reactions that are broken down so simplistically to its elements, we can use the delta H of formation for all of these things. And then really what we can do is we can just do products minus the reactants. Now we do have to multiply them by the number of moles in the balanced chemical reaction in order to get the right answer. Okay, but this is really, when we do thermodynamics, this is really what we're doing. Okay, and now I will say this: it's always going to be products. Let me get rid of that. It's always going to be products minus the reactants. For any thermodynamic value, we always do products minus the reactants. Okay, that's just what we do. Okay, so in equilibrium, we did products over the reactants, and that was always where we started from. Well, in thermodynamics, we're doing products minus the reactants. Okay, so that's a kind of a way to remember that. Okay, and so we don't necessarily have to use the formation reactions. We really can just skip to number 4 and go to the tables and tables and tables and tables of thermodynamic data. You could imagine that a lot of compounds have a enthalpy of formation. Okay, but how do we know if a reaction is product flavored? If it's product flavored, it tastes just like the product. If it's product favored or reactant favored. Okay, well, typically exothermic reactions are product favored. If you're giving off heat, reactions like to lose energy. It's not that they do it all the time, but that just means that you're more likely to get a product-favored reaction if you have an exothermic reaction. So keep in mind that exothermic is a negative delta H. And so endothermic is positive, and so typically those reactants those reactions are reactant-favored, which means that they don't typically go towards the products. If you have reactants products, only a little bit or not much at all, or they'll pretty much stay as reactants, typically. Keep in mind that word favored, though, favored doesn't mean that it's spontaneous. So that doesn't, just because something is product favored doesn't mean it's spontaneously going to go to the products. Okay, it doesn't mean that it's automatically going to do that. It just means that it's likely to do that. Okay, and we bring this up, this especially, is because delta H, enthalpy, is not a measure of spontaneity. It's a factor in spontaneity. It's just not the measure of spontaneity. It just tells us if we're favored or not favored. Okay, so let's spend a little time and see what we can do in order to see if we can apply this guy right here. Okay, so it says, what is the standard enthalpy of combustion of benzene? Now, one of the things that I think it's important for you to be able to do is write a combustion reaction. So a combustion reaction is whatever compound that you're burning, C6H6, that's benzene, plus O2 gas, okay? And that reacts to form water, H2O, and that's liquid, plus CO2, and that's a gas, okay? So a combustion reaction is always whatever plus oxygen gives carbon dioxide and water, okay? It's always what it is, okay? And it says, what is the standard enthalpy of combustion? Okay, so the delta H, and in this case of the reaction, and we can actually specifically put the type of reaction that it is, okay? This is a combustion reaction, okay? So we can either put reaction, or we could, instead of putting reaction, if we know that it's a specific type of reaction, we could put delta H of combustion, and that's going to equal, so this is the products minus the reactants. So it's delta H, the summation of the products minus the summation of the delta H of formation of the reactants. Okay? So now we can solve this problem. Okay? Well, what's the delta H of the products? Well, we have to balance the reaction first. Okay, so I'll balance it in this color. So let's see, how many hydrogens? Hydrogens, that's 3. How many carbons? So that's going to be 6. And so that's 18, that's 12 and 15. So this is going to be 15. It's going to be 15. It's going to be 15 halves. Okay? That's the balanced chemical equation. Now, to do this, I don't want to use halves. So in order to get rid of the halves, okay, that way I don't want the halves. I want the have-nots, not halves. Haves and have-nots. Anyways, okay. Okay, so I'm going to multiply all these things by 2. This is going to turn into 15. This is going to turn into 6. Oh, that one's going to turn into 2, and this one's going to turn into 12. Okay, so what do we do here? So what I'm going to do is I'm going to do my work on this, so 2, 15, 6, 12. So it's 2, C, 6H, 6 plus 15 O2 reacts to form 6. What was it? 6H2O plus 12CO2. Okay. So that's our thing. So now, in order to calculate this, we're going to do products minus the reactants. So the delta H, so let's do that. So delta H of combustion is going to equal the products, all the products. So it's 6 moles. I'm going to put that in square brackets because it's going to be 6 moles. And then H2O has a delta H of formation of negative 241.8. Okay, well that's, so then it's times negative 241.8 plus that summation sign, that means add. So we're going to add this 12 times CO2, and CO2 is negative 393.5. Okay, so that's negative 393.5. And so this here, this is our products. Now we have to, it's products minus the reactants. So now we have to do the same thing, okay, minus the reactants. So it's 2 times the delta H formation of this guy, which is plus 49. Okay, plus 49. and then plus 15 times the, oh wait, the delta H of formation of oxygen is not there. Remember, any element in its most natural standard state, the delta H of formation is 0. So even though it's kind of silly to put it in there, I'm still going to, because now I am saying that, hey, I have done the reactant, I've done the products, now I have all the reactants here. So it's products and reactants. And I think that that helps us out. So the delta H of combustion is products minus reactants. Great. So now we just have to do some math in order to figure out what it is. So let me bring up my calculator. Okay, so it's 6 times, and be very careful doing the calculations on this. There's a lot of pluses and minuses and subtractions and addings and stuff. And so when doing this, I can tell you that it's probably a math error more than it's a chemistry error. So we're going to do 6 times negative 241.8 plus 12 times negative 393.5. Okay. And so I always do things like in steps. So now this, the products, is negative 6172.8 minus the reactants, 2 times 49. Then for completeness, I guess I'll go plus 15 times 0. Okay. So then we get, so minus, so that's the reactants, or that's the products, and then the reactants is minus 98. Okay. So now we do the math here. So now we still have one more step to find the delta H of combustion. So the delta H of the reaction, in this case the specific reaction is called combustion, of combustion equals this. So negative 6172.8 minus 98. And so we get negative 6270.8. Excuse me. And what is the units of that? It's in kilojoules. So that's the delta H of that reaction. And this is the most common way that we do determine the delta H, or the enthalpy of a reaction.